All right, it's Mr. Hess. I'm back to give you another lesson here in geometry. This next lesson is going to be lesson 1.2. It's in our first module. And today's lesson is going to focus on angles. In our previous lesson, I did mention a special type of figure in geometry called a ray. A ray, of course, looks like this, where it had an end point on it, and it went on forever in one direction. Okay, if the array had a label on here with some points, maybe like an A here and a B here. Okay, when you go to name this ray, then you should always name this ray by its end point first. Okay, so in this picture, you can see it starts here at A and goes in the direction of B. So this would be ray AB. The symbol will always point to the right because we always supposed to start with the end point, so the end point should be under the end point of the symbol, see? Okay, so the symbol will always point to the right, even if the figure points to the left. Now, if I had changed things up here, though, and did this, have the ray point this direction now that is not the proper name for this ray. This time now, the ray starts here at B, and it goes in the direction of A. So this would be called ray BA. Again, the symbol, like I said, will always point to the right, even if the ray points to the left or up or down. It doesn't matter. The symbol always points to the right because you always start with the end point first here when naming your ray. I wanted to remind you about rays because rays are going to be what we use to make angles. And that's what really today's lesson is all about, is making an angle. So let me tidy up a little bit here and show you what I mean. Okay, if I take this ray now and if I put another ray starting at the same endpoint, okay, like this. Now I've got a second ray, and let's call that maybe point C. Okay, now I've created what's called an angle. Okay, an angle then is always made up of two rays that share a common endpoint like that. Now, this angle, in order to name the angle, the symbol for an angle looks like this. Looks like a little miniature angle, maybe like a little slanted L. And what's different now is the symbols we had been using previously, those symbols like for line, segment, ray, all of those went up above the letters. This is going to go out in front of it. Okay, and then imagine you're tracing this angle. So when you go to name an angle, typically you will use three letters to name the angle. One starting on one side of the angle, then you go to what's called the vertex. Okay, this point right here, where the two rays meet, a lot of times what we like to say is like the corner of the angle. That's called the vertex. Okay, but whenever you name an angle, that vertex should always be the middle letter. So it'd be as if you're tracing the angle. If I were to trace this angle, I'd come across A, then B, then C. So it's called angle ABC. Of course, there are some options then. You could have named this same angle backwards. You could have traced it backwards as well. See, so CBA. So angle CBA. Okay, the only other way that you might get more options using three letters like this is if we had more points on the board. If I included another point D on here now, okay, now I've got more options. Now I can also call it angle DBC. Or, of course, backwards, CBD. You cannot do this, though. Don't call it angle ADB. Okay, notice you've only traced along one side there. Okay, and the whole point of an angle is that, it goes off in a couple of different directions. So you want to be able to trace and include points on both sides. Okay, but you would always name an angle then either using three letters like we did there, or there is an option here. There is a shortcut. Now, this shortcut that I'm about to use, though, only works if it's the only angle at this vertex. Okay, because as a shortcut, here's our last option. We could just get away with calling it angle B. The vertex, you might say, is the most important point on our angle, because that's where it makes that change in direction, you know, where it makes a turn. Okay, so the vertex should always be the middle letter if you're using 3 letters, or if you use a shortcut and just name it by its vertex alone, then you could just use 1 letter and just say it's angle B. Now, by the way, that shortcut only works, again, if it's the only angle at that vertex. That way there's no confusion as to what I'm talking about when I say angle B. You know, if I were to do this, though, now, and have a third ray come out of here, now you would no longer be allowed to use that shortcut. Because if I said, hey, look at angle B, you would ask me, well, which angle B? We've got an angle ABC that runs there. We've got an angle CBE now right beside it that runs there. And then technically there's even a third angle that a lot of people don't think about that has B as a vertex. And that's the overall angle, ABE. Okay, so in that event, if there are multiple angles at a vertex, you cannot get away with that shortcut of 1 letter. So if you really want to play it safe, you should always use 3 letters to name your angles. Okay, but that is an option if it's the only angle at the vertex. All right, so now you know what a vertex is, what an angle is. What I've created here, by the way, you might even say is a pair of what we call adjacent angles. Think about that word adjacent. Okay, to be adjacent means that they are neighbors, side by side, you know, right next to each other, adjacent. Okay, so you can see then that this angle here that I named earlier as ABC, you know, this one, and then this angle right beside it, which would be called angle CBE. So adjacent angles in this picture would be ABC and CBE. Okay, adjacent angles, you'll notice then that they share a vertex and they share a side right down the middle here too. Okay, so you'll notice they repeat those letters, BC, CB. Okay, but notice again, the middle letter is still B on all these angles that I've named up here because they all have that vertex up there at B. Okay, so adjacent angles is just a fancy way of saying they're neighbors side by side. Okay, one other thing I just thought about as a shortcut, a way to name angles quicker. You may see, and you may have seen this before in the past in your math classes, where right down here near the vertex, they might throw in some numbers in here, you know, like a 1 and a 2. And they're not referring to the degrees. You know, degrees, as you know, has that little circle symbol for degrees. Not to mention that obviously is bigger than 1 degree. Okay, so you can kind of tell that's not a measurement being given there. But that is a shortcut now. So like when we set up here, angle ABC could be called CBA, could be called DBC or CBD. Well, that same angle that we had 1, 2, 3, 4 ways of naming, this angle could also be named, and actually that was a 5th way initially, but we can't use that anymore. But now that I've numbered them, you could just call it angle 1. Okay, and then of course angle 2 would be the same as this CBE. CBE is also angle 2. Okay, so those are ways of doing shortcuts there as well. Then you don't have to worry about, you know, if there's more than one angle sharing the same vertex like we had here. If you number them individually, you could just say angle 1, angle 2. Okay? By the way, you can't call the overall thing then angle 3. You know, you might think, oh, 1 plus 2 is 3. Let's call that whole thing 3. There's no shortcuts for the overall angle. No way, no quick way to name that overall angle. You just have to call it ABE. And it would be that full overall angle. All right, I hope you're catching on then to angles. You know, they're made up of rays. They have a vertex. There's adjacent angles that are side by side. So the next thing here that I want to cover then is the different classifications of angles. Okay, now this is more than likely going to be a review for you. So I apologize if this seems like a waste of your time, but I want to cover it real quick just to make sure everybody's seen these before. Okay, and the different ways to classify them, well, first of all, there's what we call acute angles. Okay, an acute angle is going to be an angle that is less than 90 degrees. Less than 90. So a lot of people are familiar with a 90-degree angle is what we call a right angle, you know, like a corner of a piece of paper or something is 90 degrees. Okay, so an acute angle is less than that, so it might look something like this. Clearly you can see that's less than 90. You know, if that was 90, you can see that's less. And most of these should be obvious. You could be able to tell right away with looking at them without having to measure them or anything. And a good way to remember that, if you have trouble remembering that, just remember that things that are miniature, we often say are cute. So an acute angle is a miniature angle. It's a small angle. It's less than 90. So because it's so small, it's acute. Okay, so there's an acute angle. Then the opposite of that you probably have heard about before as well is obtuse. Obtuse angles are, instead of less than 90, are going to be between 90 and 180. I would just say, you know, bigger than 90, but be careful. There are some classifications then that, like a 180 degree angle is bigger than 90, but it has its own special name. And then technically no angle can ever get any bigger than 180 anyways. So we really should say obtuse is between 90 and 180. Okay, they're the bigger angles then. You know that in a picture of it, it might look something like this, where you can see then that that where this angle was less than 90, this one you can see clearly is bigger. Okay, 90 degrees again being probably about right in there would be 90. You can see this is wider. So it'd be bigger than or wider than a corner of a piece of paper. Again, an easy way to remember this, I think, is, well, for example, when you go to your doctor, if your doctor says you're overweight, the technical term for that is obese. And, well, notice that obtuse starts out with those same letters like obese. So this is like an obese angle. It's a big angle. It's between 90 and 180. So obese, obtuse, that might be a good way to remember that one. All right, now there's technically two more classifications. Okay, and this goes back to what I was just talking about. Notice here I said less than 90, but this one was between 90 and 180. Well, if it's exactly 90 degrees, that's what we call a right angle. Of course, a right angle then is what you're used to seeing in your everyday life. Almost everything you see that's man-made typically has nice, sharp right angle corners on it. Okay, so it would look something maybe like this. Okay, and if the textbook or somebody's trying to indicate to you that this is in fact a right angle, if they want you to know that for sure, there's a special mark we could put down here at the vertex. We could put a little square box in there. Okay, so if you see the square box, that means it's definitely 90. Okay, if you don't see the square box, that doesn't mean it can't still be 90. I mean, it still could. It's just they're not bothering to indicate to you right away, hey, this is 90. Okay? But if you do see the box, that's a safe way of assuming it will be 90 degrees. Okay, and then the last category here, again, is a technical one here. It's going to cover one of the numbers I mentioned up here already, the 180. Some textbooks do not consider this an angle, though, but this textbook has mentioned it in here, and this is what we call a straight angle. Straight angle, and then to be 180 degrees, then if you can imagine this, you've got two rays. It's just you'd have a starting point here, and one ray would run this way, the other ray would run in the exact opposite direction. Okay, so that is still considered an angle in many textbooks, and it measures 180 degrees all the way across from there to there. So they call it a straight angle. As you can see, it makes a nice straight line. So that one's pretty obvious on how it got its name. Okay, so there's your classifying of angles, the different types of angles you might run into. Okay, now in our lesson the other day, I know it was a rather long one. It covered quite a bit of material. That's why it was so long, but in that lesson, if you recall correctly, I used the term bisect. Okay, to bisect something means that we are going to be taking that figure and cutting it in half. Okay, so to bisect, just remember that anytime you ever hear that word, bisect means to cut into two equal halves. Okay, a little different than the word dissect with a D. You know, in your biology class, you might have dissected different animals and stuff, and that just means to cut up into pieces. Okay, but bisect, using that prefix bi, refers to the number 2. So you can see then it means we're going to be cutting it into two halves. And in geometry, anything we talk about bisecting means we're going to cut it into two equal halves. So they have to be equal as well. Now the other day I talked about it in terms of a segment. You know, every segment has a certain length, so you could always find the exact dead center middle or midpoint. We talked about that the other day. And then that means that if I cut through that point with anything like a line, for example, then this just bisected the segment. This would be what I call the bisector, because he's the one doing the cutting. That line cut right through there. But it cut this into two equal halves, so that's what got bisected. Okay, well that was a segment. Today we're talking about angles. Okay, now this same concept can still be used though for angles. To bisect an angle just means we're going to cut it into two equal halves. So let's say I've got my angle drawn here, and I'm going to call it X, Y, Z. Okay, and then if I were to happen to bisect this, I'm going to bisect it with another ray. I'm going to take another ray and run it through like that. And then we'll call that the ray YW. So if the ray YW bisects the overall angle XYZ, then that means we're going to have some equal halves as a result, right? So in this picture, if YW bisects angle XYZ, then that means the top half of this and the bottom half of this are going to be the same. They're going to be equal. Okay, and to indicate that on a picture, whenever it comes to angles, we always mark angles with little arcs right down by their vertex. So if I mark this with a single arc, and then I mark this one with the same single arc, okay, that is an indication that I'm trying to tell you in this picture that those two halves are going to be equal. Okay, and if you remember the other day too, in that big long geometry lesson that I gave you, there's a term we use in geometry rather than saying they're equal. There's a term called congruent. congruent. So if you ever see that term congruent, that's just a fancy way of saying that whatever object I'm talking about, whether it be angles, segments, rays, lines, planes, whatever, whatever object I might be talking about, if I say they're congruent, that means that they are physically identical, so that where if you took one right over top of the other, if I had an angle here and an angle here, if I put them on top of each other, okay, they're going to match up perfectly and be the same measurement, or congruent. And the symbol for congruent looks like this. I'm trying to remember if I had mentioned that in that geometry lesson. I know it was rather long. I apologize again, but I hope my lessons otherwise might be a little bit shorter. But that's the symbol for congruent. So if I want to say this top and bottom half are congruent, the top half would be angle X, Y, W. Remember, it's just like you're tracing the angle. Okay, the middle letter should be the vertex, so there's the Y. And all these angles are centered here at Y, at this vertex. The bottom half would be called W, Y, Z. So angle W, Y, Z. Okay, now, whenever you're dealing with angles, of course, we're going to be talking, as I said earlier, about their measurements. So something else I want to point out here, that when you make a statement like this, that those two are congruent, okay, that would be the same then as saying that they have the same measure. Okay, so I'm going to put then they are congruent, or we could say that now you see that little M I put in front of the angle there? Okay, that little M means measure. So the measure of angle XYW now, congruent would be your way of just saying, hey, these shapes, these angles are the same. Okay, but if I wanted to say their measures are the same, now I instead of using the congruent symbol, now I'm back to just using regular old equal sign. Because I'm going to say, hey, the measure of this angle equals the measure of that angle. W, Y, Z. Okay, so slight different way of writing the two of them, but they really are saying the same thing. I mean, if two angles are equal in measure, then they are said to be congruent. Okay, but when you write the congruent symbol, you don't have to put little m's in front of it. It's already understood that if they're congruent, they have the same measure. All right. While we're going over all the technical terms and things you're going to need to know for this section, the next thing I want to talk about, rather than bisecting, is another angle relationship that occurs here. Sometimes when we have a pair of angles, two angles, that add up to a certain amount, we have a term we use for it. For example, we have what we call complementary angles, and closely related to that one is what we would call then supplementary angles. Okay, again, these are terms that you may have already heard about before, so I want to cover it quickly as well, just to make sure you learned that back in the day if it was covered earlier. Complementary angles then is a pair of angles a little sloppy there with my writing, sorry. Pair of angles that add up to 90 degrees. Complementary angles will add up to 90 degrees. Okay, now, technically though, they do not have to be adjacent. Do you remember just earlier in my lesson, adjacent angles were ones that were side by side, neighbors, right next to each other. Okay, they can be though. You know, you might have an angle, for example, like this that is, let's say, 62 degrees, and then another angle then right beside it, and it was, let's say, 28 degrees. Okay, if you do your math, 60 and 20 is going to be 80 degrees. These add up, though, 8 and 10 and 2 to another 10 degrees, so that's 90. So that adds up to 90 degrees. See that? So when put adjacent beside each other, they form an overall angle then that would be a right angle, right? That would be 90 degrees. However, they don't have to be adjacent, You could have a 62 degree angle like that, be right here. But then you could have your 28 degree angle and not be attached to it at all. You might have your 28 degree angle, be over here, pointing a whole different way. Okay, because they still add up to 90, they're still considered complementary. Okay, this is the more likely scenario you're going to run into when they are adjacent, but even if they aren't, you can still say they're complementary if they add up to 90. Okay, and then wording wise, if you're ever talking about any one of the two in the pair, okay, then they're said to be the complement of the other. So you could say that 62 degrees is the complement of 28 degrees. Okay? Or you could switch that around even. You could say 28 is the complement of 62. Okay? It doesn't matter, who you put first here, but if you ever want to say that as a pair that they're complementary, then you say the one is the complement of the other. Okay, now everything I just set up here for complementary angles is now going to apply to supplementary angles with one exception. Okay, in our definition here, it's again a pair of angles that add up to a certain amount. Pair of angles that add up to, and here's the difference. Complementary adds up to 90. Supplementary, I like to say, since it starts with sup like this, is the supersized version. It's kind of like back in the day when you went to a fast food restaurant, and if you wanted the extra big meal, you tell them to supersize it, make it big. Okay, well, this is the supersized version. Instead of adding up only to 90, these are going to add up to twice that. They're going to add up to 180 degrees. And we're going to deal a lot with supplementary angles. You want to get used to those. They occur quite frequently because, for example, say you've got a nice straight line like this, and then you all of a sudden split it like this. Now you've just created a couple of smaller angles. See it? You might have an angle here that measures, let's say 34 degrees there. And then this angle beside it over here then is 146 degrees. Together, if you add those up, 146, 34, I think you're going to find they do in fact add up to 180 degrees. And when they add up to 180 like this, they form, like I said, a nice straight line like that. As long as they're adjacent. Just like here. See, these are adjacent side by side. These are right beside each other as well, sharing the vertex inside. They don't have to be, though. Again, you could have, your 34 degree angle be right here, and then you could pull these apart, somehow. Maybe even have the 146 kind of looking like this instead. Going off like that, 146. Okay, those are still two angles that add up to 180, so they're still what we would call supplementary. Okay, so just to emphasize, they don't have to be adjacent, although I will say again, in real life, typically they are adjacent on these problems. And again, just like I said over here, we use that term complement to name one of the two partners. Same here. We would say that 34 degrees is the supplement, would be the term we would use. cutting off the airy off the end. See, complement, supplement. Okay, so 34 is the supplement of 146 degrees. Or, like I said earlier, it doesn't matter who you write first here. You could say 34 is the supplement of 146, or you could say 146 is the supplement of 34. Okay, so that's what complementary angles and supplementary angles are. Complementary only adds up to 90, remember? And then the supersized version adds up to 180, supplementary. All right, now I want to go ahead and try some problems then too, in case you come across some on your homework that you're not sure how to do them. I want to hit at least what I know are going to be the more difficult ones. Now, along that lines of complementary, supplementary, they'll start out with some easy ones, though. You know, they might say that angle A and angle B are supplementary. And then they might tell you some more information, like they might tell you, oh yeah, and the measure of angle A is, I don't know, let's say 74 degrees. Okay, so A and B are supplementary, angle A is 74, and then they might say, okay, find the measure of angle B. Now, you don't have to have a picture to go along with this, but, you know, if you wanted to kind of get a visual, if they're supplementary, and if they were side by side, then they would form, you know, like this, a pair that would form a straight line. In this case, I know that's not the case, though, because look at the names. Angle A and angle B. If I use a single letter to name an angle, that means that's its vertex. So if this is going to represent angle A, then this would also be called angle A. See that? So I know my picture that I drew initially here can't be the case. Instead, you know, this other bigger angle over here is separated like this with its own vertex B. But they do mention that they're supplementary, so I know they're going to add up to 180. So if they add up to 180 and one of them's 74, this one's 74, and I'm trying to find that one, well, it's pretty simple. All you have to do is take the 74 that you had here off of 180 and see what's left. As you can see, that leaves you with 106 degrees for angle B. So there's our answer, 106 degrees. Okay, be careful. They might switch this to complementary. Okay, if they had done that, or they said they're complementary. Okay, now it changes the problem a little bit. You know, if that one was 74, instead of 180, they're going to only add up to 90. So you take the 74 away from 90, in which case now you're only left with 16 degrees. So instead of 106, now it would be 16 for that angle. So it makes a big difference. Make sure you pay attention, complementary versus supplementary. Okay, some of the other problems that I am a little worried about on your homework there are some of the algebra-based problems. Let me see if I can come up with one for you here. Let's say that we had a picture like this, and we're going to call this W, J, T, and Q. Okay, and let's say that in our picture here, the measure of angle WJQ is 6x minus 15 degrees. And the measure of angle QJT is x plus 8 degrees. Okay, and after giving all this information, in the end, I want to see if you can find any and all angles up here. So I want you to be able to find the x, and I want you to be able to fill in any measurements for any angles up here. Okay, so let's start with finding x. Okay, if you look at our picture then, WJQ, that angle, WJQ, goes from here to here. Looks like a rather large angle. They say it's going to be the 6x minus 15 part. And then QJT is the other angle they give us information about. QJT, if you follow it in that order again, QJT, you'll see that's the angle right beside it here. Okay, the two angles are adjacent, like we mentioned earlier, side by side. Okay, but this one is then, appears to be smaller in our picture at least, but is labeled as x plus 8. Okay, now the one last thing that they're going to give you, they might give you this information, for example. They're going to give you the measure of one more angle in this one. They might tell you, for example, that the measure of angle WJT is 168 degrees. WJT. Do you see how WJT is the big overall angle then? Okay, so they're telling you the total is 168. Well, if that's the total, don't you see that in order to find x, we could do a very simple equation. We could just say that this part plus this part, when added together, is going to equal the total. So 6x minus 15 plus the 8x plus 8 is going to equal our total of 168. Okay? The other day, since my video ran a little long, I didn't introduce any algebra tricks that I usually share when I teach algebra. So I'm going to start to share some of those with you today. And what I want to do is take a look at this algebra problem that we need to solve here. And I want you to pay attention, first of all, to the two sides of the equation. Okay, always keep that in mind. Too many people, when they're doing algebra, make mistakes because they don't pay attention to where the equal sign is. But when you look at this problem, do you see it has multiple x's, but they're on the same side? All right, so whenever I have any algebra problems that have more than one x to solve for, I mean, it's the same x, you understand? I mean, just if the equation has more than one x in it, okay, then I look at it as one of two situations, okay? And whenever I teach algebra, I can almost always boil things down into kind of a Western type of situation. I like a Western theme to teach this, okay? And in the Old West, you know, you had sheriffs and you had bandits, you know, you know, a lot of people are familiar with old Westerns, so I could use that as a good analogy. But I have multiple x's here, and notice they're on the same side. So whenever I have multiple x's, I look for one of two situations, what I call a sheriff-bandit or sheriff-deputy situation. I'm not sure if I'm spelling sheriff correctly here. I don't know if there's two R's. I want to say there's only one. It doesn't look right, though. But anyways, sheriff-bandit, or what I would call a sheriff-deputy. Okay, now, a sheriff and a bandit are on opposite sides of the law, right? sheriff's trying to uphold the law, the bandit's the one breaking the law. So they're on opposite sides. Okay, look at our x's though. Do you see I had an x that is right there and another x that's right there? And again, the two of them are on the same side of the equation. So they're not a sheriff-bandit situation. This is not sheriff-bandit. They're on the same side. And if they're already on the same side, that'd be like a sheriff and a deputy, see? Okay, when a sheriff and a deputy in the Old West got together, they would work together. They would join forces, right? They would work together to get rid of all the bad guys, the bandits. Okay, so that's what's going to happen here. My x's are already on the same side. So when they're on the same side, they're going to join forces. So if I have what's understood to be 1x here, plus another 6 x's here, that would give you 7 of those x's. Do you see that we can do it all over again? This time with the 8 and the minus 15. What I'm doing, by the way, is called combining like terms when you were taught it in algebra. Okay, so that gives you 7x. Then these two are going to combine. Be careful. Positive 8, negative 15, or minus 15, they're going to cancel each other out. They don't, they aren't just going to join forces, so to speak. I always like to think of positive as good guys and negatives kind of like bad guys, and they cancel each other out. So, 8 of the good get canceled out with 15 of these bad, and that means that you still have more bad ones left. You have a total of 7 bad guys still left. Or in other words, 8 off of 15 is 7. Okay, but it is a negative 7 because there was more negatives than positives. All right, that equals the 168. Okay, now when you get down to this point, most of you know what to do here, at least on algebra. At this point, you always revert back to just your normal order of operations. Okay, I can't remember what all I told you in that first video about that, but that's the normal order of operations. Parentheses, exponents, multiply, divide, add, subtract. Whereas the multiply and divide tie and the add and subtract tie in order. But that's the normal order you go in. But when you do algebra, I don't know if I mentioned this the other day. I told people all of algebra is like when you lose your keys. Okay, you've lost a number. We've lost x. X is a missing number. And the number one strategy when you lose something, is to trace your steps. Okay, so that's what we're going to do here. So instead of doing the normal order of operations, we're going to be doing this backwards. So instead of PEMDAS, and this is the one exception, the P is still the first one though. So I'm going to move the P, but we're doing it backwards here. So now it's PSADME. So we still look for parentheses first. Seeing none, I move on to adding or subtracting. Okay, remember the goal is to find the x. Keep your eye on the prize, as they say. So always focus on this x right here. And don't worry about what's over here. What ends up over there is just going to be a consequence of what we do here to get the x by itself. So I see I've got a 7 and a 7. Now these 7s, though, you get rid of each one of these differently. I hope you understand. In algebra, to get rid of something, you do the opposite. So if I want to be doing adding and subtracting right now, they did a minus 7 right here, subtract 7. So I'm going to do the opposite. I'm going to get rid of that by adding a 7. Okay, but again, don't forget that these are equal or balanced, equations. So to keep them balanced, whatever you do to one side, you have to do the other. Okay, you probably heard that a million times too in algebra. Okay, so that's our next step since we're supposed to be doing adding and subtracting. These cancel. Now you're left with just a 7x. Okay, over here, 168 plus the 7 gets me up to 175. Okay, then last step. I feel like I've done something wrong here. Hold on. Nope, I'm good. All right, now I've done my adding and subtracting. This last 7 you'll see currently is being multiplied, right? It's understood to be 7 times x. So if I'm going to get rid of it, again, I've got to do the opposite. You know, just like you got rid of a minus 7 by adding 7, to get rid of a times 7, you've got to divide by 7. So that's what our final step is going to be to help us find the x at least. So we divide by 7. We're doing that last part, multiply, divide. There's no exponents on these. We'll rarely do any exponents in this class. But 7 then goes into 175. It goes in there, believe it or not, a nice equal amount. You know, it goes in this to 17, for example, 2 times. And that would be 14, carry the 3, 35, would be 5, 25. 25 is our x. Okay, so all that work to get our x. Again, it's based on the simple idea, though, of the equation where I just said this angle plus that angle equaled the total, 168. And then now that you know x, technically you could plug it back in and find each of the angles. Okay, so now we know if we plug that back in, we plug a 25 in there. Let's see, 6 times 25 is going to be 150. Minus the 15 gets us down to 135. And then over here, that's a much easier one. Just plug a 25 in here, and we got 25 plus 8. So that's just 33. And it makes sense, because look, 33 plus 135 does give us the grand total of 168 for the entire angle. Okay? Now, when you do problems like this, they can give you any kind of total they want that these are going to add up to. Okay? You just got to be able to adjust. They could even have that total end up being, like, for example, 180 degrees, which would be supplementary angles. Right? Remember, supplementary add up to 180? So you might have problems where they add up to 180 even. That just means you put a 180 there. Same thing, though. They might add up only to 90 if they're complementary. So then there would be a 90 there and there. But again, you would still solve the problem the same. Okay, so any problem like that where you've got a couple of angles that are adjacent side by side, chances are on an algebra problem like this, you're just going to simply add them up to equal the total. One more then I want to try of those, and this last one is going to involve then, it's a similar situation to this, only this time the ray down the middle is going to be a bisector. I want to try one where it's a bisector. Alright, so let's see here. Now I've got one that I could use here.